Welcome to another step down this rabbit hole of volumes in Houdini. Usually my go-to render engine for these tutorials has been Redshift traditionally, because I'm on a single workstation and Redshift is really fast on a single workstation that's equipped with GPUs. However, there is one single feature when it comes to volumes that can make Mantra the most efficient render engine. Before we dive into the intricacies of Houdini's volume procedurals, let me just explain some rather simple basics about what we're going to do. One thing we need to know is how to fill a circle in 2D or a sphere in 3D. To fill a circle or a sphere, we need to check which points lie within the circle's radius. So a circle / a sphere is defined by their respective radius. That's the distance from the center to the outer boundary. So in order to fill a space, be it a circle in 2D or a sphere in 3D, we need to check if the position that we are currently working on, right this point here, to the circle's center is smaller than the radius, then we can fill the point, or if it is bigger than the radius, and we won't fill the point. And when I do this for each and every position, I will end up either with a perfect circle or a perfect sphere. In order to demonstrate what I mean, I will drop down an environment light and a camera. Let's lock the camera to the viewport so I can move it around. And in the environment light, I will just give it our standard HDRI. Maybe crank up the light intensity a bit, like so. And then I will drop down a geo, dive in, and create a volume. Just our standard volume, and let's leave it at that size. And after that, I'm just going to drop down a volume wrangle. Wire this up, and before I start writing some VEX code here, let's just make sure our volume is called density, like so. Middle mouse on it, and I see I have a density volume here that stores floats. And what I'd like to do in the volume wrangle is I want to check if our current voxel position, that's v at p, and a vector 0, 0, 0, that's our center, if they are within a given distance to each other. So let's drop down the distance function here, and we measure the distance from our current voxel position to the center of the scene at 0, 0, 0. And we check if this is smaller than, say, 0.5, and if it is so, we will set our density value to, say, 10.0. And this is, of course, density, not desnity. And we just created ourselves a small sphere. Now, if we want to render this, what we could naively do is head to our Out tab here, create a Mantra node. Under rendering, set it to physically based rendering. And then in the render view, just hit render here. Takes a while. And now we see we have this really coarse blob here. Let me just go to the OBJ and in the environment light, enable render light geometry so we can see the background. So again, we have this kind of blocky blob here. And what happens here becomes more evident if we go into the geo node and in the volume wrangle, dial up our density to maybe not 10, but 1000. And now you can see these blocks here. And these are our individual voxels. Because currently our volume is really low in resolution, so we have only 10 by 10 by 10 voxels here. And of course what I could do is dial up the volume resolution and end up with bigger simulation times, more memory usage, and all the downsides that go with big volumes. However, there is a brilliant feature in Mantra that allows you to use this exact VEX code that we've just written here and put it in a shader, so it only gets executed and evaluated on render time, which not only means that you are saving memory because you don't have to evaluate this formula beforehand, but it also means you can arbitrarily increase the resolution of the volume down to a sub-pixel accuracy, so you will be able to render really detailed volumes. And this technique is called a volume procedural. In order to create a volume procedural, let me just close these tabs here, pin this tab, and hit Ctrl-T to create new tabs. Let's switch this tab to our Out context, and this one here to our shop context, because as of my knowledge, the volume procedural still has to be created in the shop context. So what we need are a volume procedural node here, the VEX volume procedural node here, and we will need a CVEX shader builder. And the CVEX shader builder is a node where we'll actually write our code into. So let's dive in there. And in there, it is empty yet. So let's drop down a snippet. And a snippet is really similar to a wrangle. In fact, a wrangle is nothing more than a snippet with a wrapper around to make it more comfortable to use. Let's head back to our geo here. And in the volume wrangle, let's copy this code here. Head back to our CVEX builder. And in the snippet, let's just paste this code. And what we'll have to do is we have to specify that we want to export density. So under the bindings to export tab, let's type in density. like so, and head up one level. Let's link this CVEX shader into our volume procedural by just dragging this up here in the shader slot. Now let's head back to the OBJ level, go up one level, and on the geometry, in the render tab, in the geometry tab, let's select our volume procedural here. So let's select the shop. Let's use this volume procedural here. Hit accept. And now we can see Mantra starts immediately to render and renders this perfect sphere, because now it evaluates the code that is in the volume procedural. What I could even do is, in our geometry, delete this volume wrangle here, and it will still render the sphere, because for this volume, Mantra will still execute our volume procedural. Apart from this really elaborate way to render a sphere, we can do other things with the volume procedurals. Let me just hit stop here, and in our shop context, in our CVEX shader builder, instead of this simple code for a sphere, let's drop down something a bit more elaborate. So let's get rid of this, and I want to define two floats, a value called A and a value called B. Not initialize them yet. Also, I need an integer called seed. Set this to 1, 2, 3. And as you might have guessed, we are working with a bit of noise here. So I'm going to drop down a wNoise function, which will output a Wally noise. Let's pause here for a second and explain what Wally noise actually is. Well, Wally noise results in a cell-like appearance of our noise, and I think you have seen it. You might know it from texturing or texture generation, and it usually looks like this in 2D. So to generate Wally noise, we start by randomly placing points in space, as here. And what we'd like to do is, we would like to generate a noise value, which in this example would be the brightness. So we'd like to generate a noise value, for example, at this position here. And what we're going to do to generate this value is, we'll find the closest point to that position. In our case, that will be this point here, and we calculate the distance from our current position to this point. And this is the value of our Wally noise. On top of that, Houdini can also generate values for the second, third, or foremost distant point from our position. For example, this would be the second closest point to our position. So let's use that in our procedural. And it needs our current voxel position, it needs a seed, and it'll write the resulting values into the variables A and B. And now I want to check if B minus A is smaller than a very small value, let's say 0.05. And if that is true, we will set our density to 1000 again. Let's see. Hit render here. And we can see now Mantra renders this emerging cellular structure that we just created by using a Wally noise. And you can see, yes, of course, the image is a bit noisy. We can dial up the sampling. But also you can see some artifacts, like in these areas here, for example, or here, where we get kind of voxel-like structures. And the way to get rid of them is in the Output tab in the Mantra node. Let's scroll down a bit. And we can see here something called a volume step rate. And this basically tells Mantra how finely it should sample the volume procedural. So let's dial this up to 1. And you can see on the one hand, our volume gets more dense. That is because now Mantra is sampling more virtual voxels in order to generate this volume. And on the other hand, we got rid of most of the artifacts. Still some small areas, for example here, let's clear that a bit better. But we still have some artifacts. However, they were just from the interactive sampling. Let's stop the rendering here and go back into our volume procedural here. And apart from this condition here, where we check which values our noise has, let's also check the distance again, like in the spherical setup that we had previously. So let's check the distance of our current voxel position and the center. And let's check if it is smaller and say 1.0. Hit render again. And you can see now we get an intersection of both the sphere and the noise. Let's increase this radius a bit to say 1.3. Hit render. We can see something weird happening there. Let me zoom out a bit. Because we currently get these truncated areas that look like a sphere and a cube would intersect. And it took me a while to figure out what's going on. So when we go up one level to our shop network, in the volume procedural, Mantra needs to decide for which area this volume procedural should be rendered. And if we don't tell our shader anything, it assumes that the volume procedural should only be rendered within a 1 by 1 by 1 cube around the center of our scene, which we clearly don't want. And to control this, we have to add some parameters to this shader. Let's go here to edit parameter interface, and in the render properties we want to filter for something called IFD, and we find this folder here called bounce IFD. Let's just drag it over, hit apply and accept, and these parameters now allow us to dial in where Mantra should use the volume procedural in our scene. So let's set that to explicit bounce here and dial up our min and max bounce to -2, -2, and -2 and 2, 2, 2 respectively. Hit render again, And we can see now these truncated areas are gone. Now what you can immediately do is head into our CVEX builder here and in the snippet experiment with using different noises, for example X noise or the standard noise, to create those high detailed volumetric procedurals.